Good. Welcome everyone to the 2020 APEC Groundbreakers Virtual Tour by Apaca UC. This year our event will be the biggest one ever done with 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it will cover sessions on 4 different languages. Please remember to register to as many sessions as you can, and all sessions will be available to replay as many times as you want for the next 2 weeks after the initial session date and time. You can also interact with the speaker at any time during that 2 weeks by posting questions or comments directly in the playback session page. I would like to say thanks to our Oracle user groups and Java user groups that made this event possible, and also to our sponsors, Oracle Groundbreakers and CloudDB. Now for today's session, Blockchain Through the Looking Glass by Kevin Wittek. Please feel free to write questions at any time during the session using the Q&A tab of the Zoom webinar, and the speaker, in this case Kevin, will be answering them at the end of the session. If any issues during the presentation, please feel free to contact me at any time using the chat tab of the Zoom webinar. Now, without any more delays, I would like to leave you with this amazing session by Kevin. And Kevin, I'm stop sharing my screen right now and giving to you the control.
All right. Hi. Good morning, everyone. Or I don't know at which time zone you're based. So for me, it's really early in the morning. It's super dark in here. So I was a little bit shocked when I recalculated the time zone from my side here. But all good. I had some coffee and now we're good to go. I also had some last minute Zoom problems. These kind of things sometimes happen in the virtual talks as well. But I think we are good to go now. Yes, as you heard before, like if you have any questions, just put them in the Q&A, and I will answer them at the end, or potentially also in between. So if we can have some interactivity there, I'd be happy to get in touch with you. And just to double check, my talk goes until 7:45. Is this correct? I just assume. All right. So I want to talk about blockchain, and it will be like a little bit of an overview talk, and also diving in some of the historic stuff. And the idea is that you get an idea about what blockchain is and how it relates to yourself and the technology world and in general. And I don't want to sell you anything. It should not be about hype or buzzword stuff. I just want to bring the computer science behind the blockchain, behind the technology to the table. About myself, my name is Kevin Wittek. I last year switched from the industry to academia to do my PhD. Before I was a software engineer in a cybersecurity area, and I switched now to academia, to the university, to do blockchain research, and I'm heading the blockchain lab at the Institute for Internet Security at the Westphalian University of Applied Sciences in Germany, Gelsenkirchen. But I'm also at the same time still a consultant and a coach for general software topics, things like software craftsmanship, etc. And I'm in the Java community. I'm mostly known for being one of the maintainers of the Test Containers open source project. I'm also an Oracle Groundbreaker ambassador. That's also why I'm here today at this virtual meeting. And I'm now involved in a lot of different technical steering groups, etc., of different blockchain communities and work groups. So the name of the talk is Blockchain Through the Looking Glass. And this is kind of a quote from a title from a book from Lewis Carroll, who is in Germany most known for his Alice in Wonderland stories. But Through the Looking Glass is the follow-up story. And in this story, Alice finds out that behind her looking glass, behind her mirror, there lies a different world where rules are different, and she steps through it and discovers this new world. And my idea is that this talk goes through this mirror, through this foggy, buzzwordy stuff of blockchain into the realities that are behind them, and give you some more insight into what blockchain really is. And for this I like to dive into the historic context as well, and like to spin a narrative how I see the historic context of computing with regards to blockchain. And here we see Ken Thompson and Dennis Ritchie in the 70s back then when they were inventing Unix, basically. And I think it's possible to spin a narrative from the time-sharing systems of old to nowadays blockchain networks, which one can say are kind of a world computer in a certain way. At least that's how I like to understand it. And in the 60s, when they were envisioning those time-sharing systems that are the foundation of Unix, they were the people from MIT, from Bell Labs, they were thinking to model those computing resources after already public utility resources, after things like a telephone network or the power grid. And the idea was that people would use this distributed computing power depending on their resources needs. So in the 60s, when they invented the time-sharing operating systems, they were thinking that all the universities would have those mainframes or whatever computers they had at that time. They put them together in a network, and everyone would only use the resources they need at the time they need. So very, very visionary already in the beginning. And of course, it changed, and everyone had their own mainframe actually in the cellar and were using their own supercomputers or mainframe or whatever. But the topic of utility computing and networking moved on, and then with the ARPANET that later became the internet, and thanks to Tim Berners-Lee from CERN, the World Wide Web, we had the next level of a distributed utility resource. The internet, the network, is a utility resource for us all to use in a shared way. Yes, 89 we had the World Wide Web, and then the move to cloud computing that was started by Amazon AWS with EC2 in beginning of the 2000s or middle of the 2000s is again a next level of these utility computing, so to say, and already better models just pay for what you use. But at the same time, this cloud computing movement didn't lead to necessarily a bigger decentralization of the internet. So the internet itself is a very decentralized system, but cloud computing to a certain degree currently centralizes computing power again, and centralizes power in general to a certain degree, which is something we should be aware of. And now, blockchain has to some degree a potential to change this, especially public blockchains. And with the Bitcoin network that went live in 2009, we have basically a decentralized state machine, a self-synchronizing decentralized state machine. That it is at its core. Of course, you use it for payment transactions, but in its core, it's a decentralized state machine. And in 2015, with the going live of the Ethereum network, we, in addition to having this decentralized state machine, we have a quasi-Turing complete virtual machine. So we have now a decentralized world computer that is programmable and can execute our code in a decentralized fashion. And that is, from at least a technical and visionary standpoint, a pretty cool thing, I would say. And moving forward, we will see and need some network of networks things like bigger interoperabilities in blockchains, if we look at least in the blockchain topic. Blockchain is always built into a narrative context of trust and trust architectures. And in the first paper, like that is about Bitcoin, from Satoshi Nakamoto, which of course is a pseudonym, he says the following thing, or we have the following sentence: we have proposed a system for electronic transaction without relying on trust. So it's people like to tell you that if you use blockchain, you don't need trust anymore. But I would say this is not correct. People say this, but I say it's not correct. So what happened is that blockchain enabled a new trust architecture in addition to the known trust architectures. So we classically have something like a peer-to-peer trust. If you trust another person directly, we have a Leviathan trust where we trust in certain rules and laws of society. We have trust in intermediaries, which we use every day when we execute normal banking transactions, where we trust the banks as the intermediaries. And now with blockchain, we have a distributed trust where we trust the correctness of the technology implementation and their protocols. So, and then that all participants in this distributed system also in majority act honestly, and therefore trust gets shifted. So we still need trust. Blockchain is not a trustless system. We're just shifting the trust into the technology. And now I can bring this nice quote from Ken Thompson he gave at his Turing Award lecture in '84, Reflections on Trusting Trust. To what extent should one trust the statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software. And this is back then was correct, and it's still correct, true. It's still correct today, and especially also with regards to blockchain. So the blockchain people, they can tell you what they want. In the end, you either have to trust them or the people who wrote the code, or you have to check the code itself. Blockchain by itself is not a trustless technology. This is a lie. You are trusting something. Like the human social concept of trust, it's still in play here. And we know the saying from Linus Torvalds, given enough eyeballs, all bugs are shallow. Yeah. So that says basically, if everything is just open source, we will discover all bugs. We will discover all security bugs. We will discover all backdoors. But I think the past has us seen that this is not necessarily true to 100%. We have seen extreme bugs in OpenSSL. Yes, they have been found, but they have been there forever. And the open source industry itself has a lot of problems to scale to the needs of the professional industry that is taking a lot of what the open source community produces for granted without always giving back enough resources to bring those projects to a next level, next quality level whatsoever. But this is a topic for another talk. Okay, so of course, when you talk about blockchain, you have to a little bit touch the topic of cryptocurrencies, because Bitcoin and cryptocurrencies is the technology that brought blockchain into adoption and into the conscience of the industry and society. If we look at Bitcoin, the paper was published 2008 anonymously or pseudonymously on the cryptography mailing list. And in 2009, the Genesis block, the first Bitcoin block, was mined, and therefore the network became live. And we saw a certain rise of transactions per month. We see this in the graph here. So now we are currently at a volume of 10 million transactions per month. There is a certain growth in the system, but compared to credit card transactions, this number is still pretty small. Yeah. So it's still a niche system, but it is a live system and a productive system to use. For certain use cases, Bitcoin is a good system. And what is also known, of course, to the people and something they question about Bitcoin is the volatility of the value of the currency. So in the original papers, Bitcoin is a very technical concept, and it was never thought about how people would speculate with it, like they do with company shares or whatever, like holding and selling and trading Bitcoins. This was not really envisioned in the original technology idea. And therefore, this behavior of society and the users changed the way how Bitcoin acts. And then we had this big inflations. We had big inflations of value and then dropping, like basically connecting the normal financial market with Bitcoin made it a speculative object. And Bitcoin is not a good fit for this kind of system, for the speculative system. Therefore, it's not super effective right now to use. And yeah, but it's like it is. So people can earn money by speculating with it, and that's why they do it. And beside Bitcoin, we have, of course, many new cryptocurrencies, and every day a new one spins up, because inventing your own cryptocurrency based on Ethereum, for example, takes like 10 minutes. You can just use existing software, implement your own cryptocurrency, an ERC20 based token, and then you're good to go. You have your own currency. Wow. So it's easy to invent cryptocurrencies nowadays based on existing technology. And yeah, the most famous ones are still Bitcoin and Ethereum, and the most widespread use with the highest market capitalization, and many others we have. We have sometimes forks like Bitcoin Cash being a fork of Ethereum, etc. So the more interesting stuff, for me at least, are the technical properties of the underlying system, in this case of Bitcoin. And I like to look into Bitcoin because Bitcoin is a bit more simple than other blockchain implementations, and therefore certain things and concepts are easier to understand. So in its core, it's a decentralized peer-to-peer network. So we have different nodes in the Bitcoin network that communicate with each other using peer-to-peer protocols, like classical peer-to-peer protocols you would formerly have seen in things like file sharing, for example. And it's used to implement digital cash as a use case. And the whole core idea of all those blockchain things is the concept of a public distributed ledger. So that's why we call blockchain in general also distributed ledger technology nowadays. And a distributed ledger is nothing but a publicly readable append-only transaction log. You can think about it like this. And then, of course, we have this consensus topic that we always talk about with regards to blockchain. And the Bitcoin one is proof of work based. I will talk a little bit more about proof of work in a couple of slides. And this consensus algorithm is by which the Bitcoin network synchronizes on a certain state. And in this case, the proof of work consensus underlying gives it certain guarantees. So it becomes Byzantine fault tolerant against less than 50% malicious actors. That is a pretty good degree of Byzantine fault tolerance. Byzantine fault tolerance is a property of distributed systems. It's from a Leslie Lamport paper, I think, and it is an general property. It's nothing blockchain specific. So you can have in all kind of distributed systems, you have this property of Byzantine fault tolerance. But you still can attack it. So there have been attacks in the past, 51% attacks, where you control 51% of the network, then you can execute attacks basically. And then another clue is this incentivization by dynamic transaction fees. I'm not going into too much detail because I want to show some code also to you in a bit, especially with regards to the proof of work stuff. But first, I like to a little bit go one step back again and give more historic context to blockchain and the history of blockchain as a data structure as well. So many see this paper by Satoshi Nakamoto from 2008 as the start of blockchain. But if you dig a little bit deeper into the history of cryptography and distributed systems and digital payment, I think you can link it back to the 80s. And in my opinion, like some other people might have different opinions, but in my opinion, the dissertation paper by David Chaum is probably one of the first works describing this data structure of chaining blocks together by using hashes. So David Chaum also was in the cryptography scene very, very much from the beginning. Very involved in digital cash topics. He had his own company, DigiCash, I think was the name, following more centralized approaches than Bitcoin, but also strong cryptographic approaches. And in his dissertation, he computer systems established, maintained, and trusted by mutually suspicious groups. He describes this concept of chaining blocks together by its hashes. And he references another paper from the 70s, from a German engineer, mathematician, Horst Feistel, cryptographic coding for data bank privacy, that is more related to encryption in this case, but it is already also like talking about concepts of chaining blocks of data together so that they enforce each other in their securities and integrities, and then you have a more secure single block. So the history of blockchain is older if you dig deeper. And in a nutshell, that's the data structure, how we can look at it. So let's look at the upper image. We have a block that consists of a couple of items. So just in general, not in Bitcoin specific, in general. We have a block with certain items. This block gets hashed. Then this hash gets combined with the hash of the previous block, and then we calculate the hash of this thing, and then we have the hash of the block in the chain. And then if we get a new block, we take the hash of the former block as the input, hash this block, and then we have a new block. So we chain them together by their hashes, and thereby every new block enforces or strengthens the integrity of the former blocks, because you can't change them and their content without changing all following blocks, because you have to recalculate all those hashes. So that's the idea of chaining things together in a blockchain. Now in Bitcoin, the data structure is a little bit different, a little bit more specific. So the items are transactions in this case. And then we have something that's called the nonce. And the nonce is a solution to the proof of work. And we look into this in a bit. And let's go to proof of work and what proof of work is. Proof of work is also older than Bitcoin. It has been first envisioned in the 90s in different papers, mostly for combating junk mail. That was the idea. So email is mostly a free resource. Everyone can use the internet to send emails basically for free. So once you send out the email, the network will deliver it for free for you. And that's a problem, because now malicious actors can send out junk mail and spam mail without paying for it, basically. And that's why we have the problem with junk mail. And different researchers thought about how to combat this problem. And they basically thought, okay, people should pay with computing resources to send an email. And then there's some way to prove that they computed it. So this proof of work was established back then. And for a single user, proving that they invested these computing resources is basically not a lot of effort. Like it takes a couple of seconds, or actually fraction of a second, to perform this proof of work. But if you are sending out millions of emails as a junk mail provider, then it becomes expensive for you. So shifting the costs, basically, depending on single usage or mass usage. And then the implementation that's now also used in Bitcoin is the Hashcash proof of work algorithm, invented by Adam Back in '97. And it's exactly the system that is used in Bitcoin. It was also envisioned for combating junk mail. So it's called Hashcash. Yeah, so we have already this cache thing, but the cache part of it is paying for sending the email. And the idea is that we have to find a partial hash collision. This is a solution to the proof of work, a partial hash collision. For a SHA-1 in case of Hashcash. And the hash collision you want to find is a certain number of leading zeros. So you want to find a hash that, for example, has 5 leading zeros. This is a partial hash collision you want to find. And you calculate the hash on concatenating some elements. Like here we see the example. This is a header you would add to your email. It has some values based on the content. Okay, they are fixed. They are inferred from the content you are sending from the email. And then you have this counter thing. And this counter is the only parameter you can change. And finding a counter value that finds this partial hash collision is the solution to the proof of work. Yes. And that's exactly how it works in Bitcoin as well. And let's check how it looks if we implement such a blockchain ourselves in Java. Whoops, sorry, this is the wrong project. Okay. All right, so I just wrote some easy sample code here. This difficulty is the partial hash collision we want to find. So 4 leading zeros. Now, this is a block class. Our block consists of some data, the hash of the previous block, and the nonce, which is initially 0. So now we can create a new block with some data and the previous hash, thereby linking them together. So this is building the chain in our case. And that's how we use it here. So we create a new block, then we have to mine it. Then we can add another block. We add the hash of the previous block to it, and then we have to mine it also. Okay. So what we now have to do is the following. When we want to mine, we calculate the hash of this block. The hash of this block is a concatenation of, in this case, the previous hash. I just put the data in there, but you could also have the hash of the data or something like this to make it smaller. So I concatenate the previous hash, my data, and the nonce. And then I calculate the hash of this. Yeah. And now I want to find here, this is my mining algorithm, my proof of work algorithm. I want to find a hash that starts with my difficulty, which is 4 leading zeros, which means the partial hash collision has been found. If I did not find the partial hash collision, I'm increasing my nonce variable by 1. And by the way, how cryptographic hash functions are distributed in their values, it's okay to just brute force by incrementing by 1. There is no other strategy that makes me find this partial hash collision faster. So I can just try out all values from 0 to whatever until I find one. If there would be another strategy that would be faster, it would mean the cryptographic hash function would have been broken, and then you would need another cryptographic hash function. And if we just check how this performs here, yeah. Okay, so we see for finding this partial hash collision with 4 leading zeros, mining the first block takes 600 milliseconds, the second block 300 milliseconds. And here, by looking at the nonce value, we know how many times this hash has been calculated and how many values have been tried out. So in this case, 200,000 times. So we also had to calculate 200 SHA hashes. So it's a little bit expensive already, yeah? And now this takes a couple of milliseconds. If we increase the difficulty by 2 zeros, yeah, so the order of magnitudes more difficult. Let's see if it even returns quickly now. If it calculates forever now, then I will decrease by 1 zero. So we already see I could increase now the difficulty, and it becomes extremely hard for my computer to find this partial hash collision. And this is built into Bitcoin as well. So Bitcoin has a dynamic difficulty, so it can increase the difficulty if more miners participate in the network. So it has a dynamic way to, that takes too long. Let's decrease by 1 zero. Okay. Okay, 5 leading zeros. Now we are over 1 second. So much, much more expensive already. And we saw 6 leading zeros. It didn't even finish now in the demo here. And now why in Bitcoin's case people do this proof of work? Because by performing this proof of work, thereby mining new blocks to the network, for the network, the miners who find the first new block gets incentivized by getting a part of the transaction fee of the Bitcoin transaction. This is the how the people are incentivized. And the whole idea of Bitcoin is that the money, the value you can generate by being an honest participant in the network is higher than the money you could get by attacking the network. So it's a very, very cool concept. And that's the cool concept of the proof of work in Bitcoin. And yes, people say like, oh, but it uses so much energy, etc., etc. Yes, it uses so much energy because of this speculative nature it has become, and of people building this big mining pools and so on. This was not the core idea back then. So it was more of like a prototypical concept. And this high energy usage is something inherent to Bitcoin. It is not inherent to other blockchain technologies because they can potentially use other consensus protocols. But there are different kinds of blockchains nowadays. So the hardliner community, blockchain community, would say a blockchain needs to be open, borderless, neutral, censorship resistant, public. So only public networks are real blockchains in their opinion. In reality, we nowadays see that the realities of blockchain technologies are more of a spectrum. And we have those very public open blockchains like Ethereum and Bitcoin. that are public networks, but we also see private, or you call it normally private permissioned blockchains, for example, that are used in banking, like bank-to-bank interactions. They are using this technology Ask Recorder, and these blockchains, they are not open for the public to see. They are only open for the participants of the networks, which are just the banks. Or another technology, Hyperledger Fabric, that is very often used in an enterprise concept. It's also a private permissioned blockchain, meaning not everyone can read what is happening in the blockchain, and not everyone is allowed to submit and execute or mine transactions. But those closed blockchains can use different consensus technologies that are much cheaper. So they are not public, therefore they can put trust differently in their trust architecture. They can trust the entities operating the nodes. Because in Bitcoin, everyone can operate a node. If you have a private blockchain network, only the people you onboarded can control it. So you can give them more trust. And that allows you other consensus protocols, like example, proof of authority, which is actually as cheap as operating other distributed systems. Then blockchain isn't that expensive anymore. Depends on your use case and the trust architecture you need. So one topic I want to quickly at least touch, and I want to show you mostly code, is the topic of smart contracts that is nowadays also always connected to blockchain. And I'm not diving into the history of it because we're running a little bit out of time. Whoopsie, yes. But they have been envisioned in the 90s by Nick Szabo originally, and it is the idea of code automatically transacting business transactions, executing business transactions, and we have a lot of code, of course, nowadays that automatically executes business transactions. Not only they are so-called smart contracts, but so he in the 90s already, Nick Szabo gave the example of a vending machine. So the vending machine has code to automatically perform this business transaction. So if you put in money, you get out the Coke or whatever. So this is a primitive idea of a smart contract. Nowadays, when we say smart contract, we mean, of course, code that executes business transactions in a distributed system, actually in a distributed ledger. And the most famous technology for this is Ethereum, which has been envisioned in 2013 by Vitalik Buterin, and then 2014 implemented by Gavin Wood, who is a really cool guy. Before this, he was doing his PhD on audio visualization, so crazy, and now he's in this blockchain domain. And yes, Ethereum brings to this synchronized state of Bitcoin now also a Turing complete or quasi Turing complete virtual machine that is programmable using a certain language. And by this way, using the smart contracts on this Ethereum network, you can develop something we call DApps, decentralized applications. And now, what is a smart contract? Let's look at realities. So smart contract is also just code, is a program that gets deployed on an Ethereum or in a blockchain network. And that's how it looks. And in a nutshell, it's very similar to object-oriented programming. Just you deploy your objects into this distributed network. So we have this contract class here, and not class, we have this contract here. And you can very much think about it like a Java class. It's now the storage contract, and can store a number, and then others can read the number. So super simple. It's like the hello world of smart contracts. And if you deploy this contract onto an Ethereum instance, you get a living deployed instance of the contract you can interact with. People can save values there, and other can retrieve the values. You have a rich state of all values that have always been in this contract. And it is like acting then instantiating an object and interacting with it. So for me, smart contracts are a way of distributed object-oriented programming. That's how I like to see it. And this is Solidity. Solidity is a language, and it gets compiled into Ethereum bytecode and then executed in the Ethereum network on Ethereum virtual machine. A little bit similar also to Java and the Java virtual machine. So those topics I'm jumping a little bit above. But let's look into this. And this is the last thing I want to show you. It's called Web3j, and it is a Java library for interacting with Ethereum. And so what I have here now, I'm having the Solidity smart contract. Yeah, the same we saw before. I now have a in my Maven, I have a Maven plugin, Web3j Maven plugin. This brings me this task here, generate sources. What the generate sources does, it compiles this Solidity smart contract. It generates a Java class, a Java proxy class that contains the compiled contract, and then constructors and functions to interact with this smart contract once deployed. And then those functions are actually like remote calls into the blockchain network. But we have a very nice API, very nice clean facade to interact with it from Java. And if we want to interact with it now, really, let's look here, Web3. Oh, no, wait, we have to check in the Groovy example. I'm not explaining what Groovy is. It's another JVM language, super cool, very nice to do some scripting in Java JVM world. So here we have a script where we want to interact with a smart contract. It would look the same from Java, so Groovy Java interoperable. First, I have a locally running Ethereum network here. This is Ganache, and you can use it to spin up a Ethereum development environment very easily. Also, they have Docker containers, etc. And now these are different addresses, different accounts I have on Ethereum. Now I have to take this private key. Okay, so I hereby say this private key is not secret anymore. Never use it anywhere in production. It's just for development purposes. And we have to put it in here. Okay, and now what I'm doing here, I'm connecting to this locally running Ethereum network. I'm creating a credentials object by using its private key. So blockchain always uses public-private key cryptography for authentication, basically for signing transactions and all interactions. And then I'm taking this proxy class I generated. I can deploy it like this, yeah, using my Web3j client, which connects to my local Ethereum network and these credentials. And then I have to execute it. I can send it. I can send asynchronously, whatever. But this is a call over the wire, basically. And now I have a deployed instance of this contract, like an instantiated object. And now I can interact with it. I can call the functions on the smart contract, like retrieving data, like changing data. That's basically what I'm doing here. Here are two more values. I'm not going in detail into this, but they are the gas I'm providing for executing or interacting with the smart contract, because you always have to pay a fee, the gas fee, for resource usage, because executing this code takes resources and you pay this by gas. Gas is the concept in Ethereum. It's a cool concept, but I don't have the time to go into this now. So yes, we see in the beginning, we have nothing on the ledger. If we interact with the smart contract and store something, we get the value on the ledger. So yeah, all good, how we expected. But then we also see here now the history of transactions. So here we can see what happens, that someone interacted with the smart contract and sent data in its parameters. The data is hashed or like binary encoded, but actually everything is public. So all interactions with your smart contracts are public. That's something to keep in mind when designing your applications to interact with smart contracts, especially public smart contracts. So there's nothing secret about it. If you would do voting, people like to implement voting on blockchains as a use case, yeah, then it would be always public voting, unless you employ very, very other, much more complex voting schemes. But the naive voting would always be public voting. So keep this in mind. All right, so I'm over with my time, I fear, also because I started a little bit late. Sorry for this. So yeah, We can't go into all the other topics. With regards to Oracle Cloud and blockchain, there are different offerings inside Oracle Cloud that provide you with blockchain features. So we have Oracle Blockchain Platform, that is a platform as a service based on Hyperledger Fabric. We didn't look in Hyperledger Fabric now, but it's one of the blockchain technologies that is always used for those enterprise projects and in-house blockchain use cases or business-to-business blockchain use cases. It's a nice open source technology. It's backed by very big players, by Linux Foundation mostly. And what is very important for me is that it supports hybrid networks. And hybrid networks means I can connect my Oracle Hyperledger Fabric with Hyperledger Fabrics from my partners that maybe run in Amazon, in Azure, and whatever. Because nothing is worse than a blockchain, a decentralized system that is just running in a single cloud vendor instance. So you should think about this resilience and really distributing your blockchain if you want to go the blockchain architecture way. And the other thing is more like cute, but is cute. Oracle 20c, Oracle database, has blockchain tables as a feature that then makes this table append only, chaining the rows using cryptographic hashing. So now one would say this is not a blockchain by most definitions, especially not regarding these 5 pillars and the concept that it's a decentralized system. It is not. But maybe this is sometimes the use case you just want to have this cryptographically hashed and chained data structure that is append only, and then go with Oracle blockchain tables. All right, thank you very much. I hope there are some questions. Maybe I'm happy to engage in further discussions. These are sponsor links mostly for my for our test containers open source project. If you're a test containers user, happy user, check it out. Maybe your company can sponsor $5 to our open source development efforts. And thank you very much. Happy to talk here. I hope we can see each other in the future in person, maybe. Yeah.
That's fantastic. Thank you so much for your session today. I cannot see any questions in the Q&A at the moment, but your session will be available on playback for 2 weeks. And everyone watching the playback can also post questions and interact with you. You'll be notified when the people post anything on your session. Thank you so much, Kevin, and thank you for sharing your knowledge with the community.
Yes, great. Thanks for having me. Yes, I'm happy to engage with anyone who is interested to talk or discuss blockchain topics. Whatever, just shoot me a message on Twitter or something.
Thank you so much. Have a wonderful day on your side, and we are almost close to the evening right here.
Yes, my day is just starting. All right. Goodbye, everyone. Have a nice day. Bye-bye.